start now. Good morning or good afternoon, everyone. So welcome to the last day of the workshop. Today we are going to discuss dark matter and their detection. So the first speaker of this session is Jongcheol from Chungnam National University. He will going to talk about detecting superlight dark matter with a graphene Joseph junction detector. The talk time is 25 minutes and 5 minutes for questions. I remind you, and the 5 minutes remains.
Okay, thank you. Then can I start?
Yeah.
Okay, so yeah. First of all, thank you guys, especially Changsa for inviting me. Okay. Today, I would like to introduce a new KB range superlight dark matter type detection strategy, adopting very recently invented graphene-based Josephson junction technology. Yeah, I will introduce what is graphene-based Josephson junction technology. This work is based on my recent work, appeared on arXiv. This work is done in collaboration with student team in Texas A&M in the USA and Kim Chung Pong in radio BBM technology in the USA and Hirori in Hwang University in Korea. Actually, among these people, these last two, K. Pong and J. Lee, they are condensed matter physicists, not particle physicists. Yeah. So yeah, as you can easily guess, based on my talk title, my talk is quite deeply relevant to condensed matter physics side. So that's why I have to collaborate with some condensed matter physicists for this one. Okay. Okay, let me start with these very famous figures. I'll not discuss anything about this one. As you know, the evidence of dark matter has been supported by lots of observation evidence. For example, gas rotation curve, CMB measurement, graphene lensing measurement, and so on. So currently, understanding the nature of dark matter is one of the most important puzzle or problem in physics. So, but for the dark matter problem, we already have a very well-known classical solution, the so-called WIM. The WIM paradigm naturally results in weak scale mass with weak scale coupling. Of course, as you know, epsilon is one of the another classical solution for the dark matter problem. This one is already covered by Luca Pessinelli on Wednesday. Okay. However, there's some big problem. Previously mentioned all of the observation on dark matter are just based on gravitational interaction of dark matter. So, to understand the practical nature of dark matter, diverging efforts for WIM search are already done or ongoing. However, unfortunately, we have not observed any firm signal of WIM yet. Such null observation at conventional dark matter search experiment motivate us to have a kind of another big question. Is WIM the only solution for the dark matter problem? As you know, the answer is of course not. Actually, the possible dark matter mass range, the possible dark matter mass of dark matter ranges from 10 to the minus 22 electron-volt to 100 times of the solar mass. Depending on dark matter mass range, we have various dark matter candidates. For example, in this ultra-light dark matter range, one of the very well-known candidates is Axion. For example, in this sub-MeV range, so-called superlight dark matter mass range, star neutrino is one of the well-motivated dark matter candidates. Of course, this weak scale in this weak scale mass range, WIMP is the most extensively studied category among these various dark matter candidate categories. So we should broaden our point of view, not limited our point of view within this WIMP mass range. Among these six categories, the first one is covered by Luca, and this WIMP candidates already mentioned, covered by Disto, and super heavy and primitive black holes are covered by previous speakers. So I will focus on this light dark matter range in this talk, especially super light one. Before going further, I'll briefly mention on this light dark matter mass range. In order to avoid overproduction problem, light dark matter having sub-GeV mass requires light new mediators for thermal pressure. You can easily estimate required mass for this new mediator based on this kind of simple estimation for dark matter annihilation cross section. So for the typical thermal pressure production mechanism, to get required light relic abundance with this mass range, the required mediator mass should be less than typical weak scale mass. So actually, there's some other possibilities for to avoid this overproduction problem with this sub-GeV mass range. So many people suggested lots of new dark matter production mechanism, including fragile, cannibal dark matter, co-decaying dark matter, semi-annihilation, SIM, and so on. And also, in addition to this dark matter production mechanism, there are various light dark matter mediator scenarios motivated by several experimental observations. For example, 511 keV gamma ray line from X-ray line from Keller central region, or mu G-2 discrepancy between observation and theoretical calculation, and so on. So that means this sub-GeV light dark matter range are quite well motivated by theoretically and at the same time experimentally. Such light messages are although rich for conventional direct dark matter direct detection experiment based on nuclear recoil, because assuming this mass with typical dark matter velocity, we can easily estimate the expected dark matter kinetic energy. The expected energy is less than kV. However, as you know, typical dark matter detection detectors for nuclear recoil, they can just have energy threshold above kV. So that means this kinetic induced by this kinetic energy, recoil signal induced by this kinetic energy cannot be seen in any typical dark matter detection experiment. Therefore, new ideas for this low energy threshold with electron recoil strongly required. For example, some people consider this kind of possibility, ionization of some particle by electron recoil, especially semiconductors, because semiconductors are well studied, and also semiconductors are particularly promising target material because their typical energy band gap is order of electron volt. So their typical band gap is less than this kV recoil energy. So this is one possibility. Another possibility is ejection of electrons from graphene or carbon nanotube target, or evaporation of equated helium by nuclear recoil induced one. There could exist another category of such mechanism for this light dark matter. One possibility is cosmic origin boosted dark matter coming from some heavy particle annihilation or decay, or some electron or neutrino-like particle induced energetic particle, energetic dark matter. So in the case, we can see this kind of energetic document signal within some large volume detectors, for example, Super K, Hyper K, or Ice Cube, or Dune, or something like that. Another possibility is we can produce this kind of light dark matter efficiently using particle beam, proton beam or electron beam. So through some fixed target experiment, we can produce dark matter beam. So if you place some dark matter detector along this line, we can see this kind of energetic dark matter recoil signal within this detector. So these figures show the current status of light dark matter direct search through dark matter and electron scattering. Left-handed panel show the result. In the case of heavy mediator, the heavy mediator means the mass of mediator is larger than typical momentum transfer. The right-handed panel show light mediator case. This light mediator means mass of mediator is lighter than typical momentum transfer. So as you can see from these two panels, up to around 1 MeV region, we already have lots of good experiment search for scattering between dark matter and electron decoy. So for example, some experiment can touch the typical freeze-out net density parameter line, or in near future, this kind of experiment can touch neutrino background region, even for dark matter and electron scattering scenario. Okay, this is the current status of light dark matter search. Then let's move on to the main focus of my talk. The super light dark matter with KB range mass is the main focus of our work. There already exist various well-motivated models and exotic observations for super light dark matter. For example, sterile neutrino or mirror neutrino dark matter, exino-gravitino dark matter, epsilon-like particle, and so on. And also we have lots of motivation based on exotic observation. For example, 3.5 kV X-ray line observed by XM neutron and so on. And also there is another very brand new exotic signal reported by Zeno-Wanton collaboration. Zeno-Wanton collaboration reported they observe KB recoil event access for electron recoil. To interpret such access based on dark matter recoil, we need very energetic light dark matter. For example, KB dark matter with quite relative velocity can give this kind of signal. So that means this KB range super light dark matter are also very well motivated. However, as you know, in the case of the sub-MeV dark matter, expected recoil energy is less than electron volt, even for electron recoil with typical velocity 10 to minus 30 times of spheroid. So new ideas for very low energy threshold are essential for super light dark matter direct detection, and several ideas have been suggested. For example, superconductor target with TS or MKR sensor, and superfluid helium target with TS or MKR sensor, or 3D Dirac material target, polar material target with this kind of sensor, or superconducting nanowire single photon detector. In this case, superconducting nanowire single photon detector is behave as a target at the same time detection device. Okay. Actually, I wanna very briefly mention on technology mentioned in my previous slide, TS and NKID SNSPD sensor word detector. So Actually, they can be usually used for application experiment requiring sensitivity to if you count on the sensitivity as the frequency range of detectable photon, then the frequency range is from X-ray to high infrared. So this frequency corresponds to at best energy threshold of order of 10 milli-electron-volt. Actually, those kind of TS sensor or MK sensor or science sensor, actually they are well developed in the laboratory in their respective energy band, around sub-electron-volt, around 10 milli-electron-volt, around 100 milli-electron-volt. However, for the sensitivity to less than milli-electron-volt, so those kind of technology need further R&D because they cannot reach sub-milli-electron-volt energy threshold up to now. So, okay. However, in our work, we propose a new super light dark matter detection strategy adopting graphene-based Josephson junction microwave single photon detector. This graphene-based Josephson junction detector is a kind of state-of-art technology because this device can have much lower energy threshold up to 1.1 milli-electron-volt. I briefly explain what is a graphene Josephson junction device. This device is consist of a pseudo monolayer graphene. Here looks like some honeycomb-shaped wiggle. This is a pseudo monolayer graphene. This monolayer of graphene sheet have two sides of this graphene sheet are joined to superconductor. Here, like this way. Then forming superconductor and a kind of normal metal and superconductor junction. But here, graphene behave a kind of very similar to normal metal, something like that. And then there are to protect this graphene is encapsulated within this HBN material. Then actually, then if some energy is deposited in this graphene sheet, then the Josephson junction is triggered. So this is a typical working mechanism of this graphene Josephson junction device. Actually, this graphene Josephson junction single photon detector was proposed ideally covering from near IR to microwave about 3 years ago. And then Kim Chu-pong and Kirul and their collaborators, these two guys are our collaborator, they have demonstrated experimentally that this GJJ microwave bolometer can have sensitivity to 0.1 milli-electron-volt energy deposit. And then their result is appeared on Nature very recently. And currently, this GJJ single photon detector is under testing in the laboratory because in this work, they, as a first step, their device as a work very well as a bolometer, not single photon detector. So now they are testing their device is also very well works very well as a single photon detector. Okay, so this figure with this figure I'll show the basics of detection principle with using this graphene Josephson junction for light dark matter detector. So the incoming dark matter can scatter a pi bond free electron within this graphene sheet, and then some portion of their kinetic energy is transferred to these electrons, and then recalling electrons are heated and thermalize with nearby electrons rapidly within some at the level of picosecond through electron recoil. Then due to this thermalization, then when injection energy raises the electron temperature in the graphene sheet, and then this kind of calorimetric effect can switch the zero voltage of Josephson junction between these two to some resistive state with appropriate level of bias current. To the best of our knowledge, no device ever known have exhibit the sensitivity of this level practically. So the GJJ device is a kind of one of the best sensor to this kind of very tiny energy deposit. So if we estimate with this KB Stockner mass, the typical kinetic energy is milli-electron volt. So if some portion of this kinetic energy is transferred to electron, then the transfer energy is above energy threshold of this device. So we can measure this kind of recoil signal using this device. This is the basics of detection principle. Okay.
You have 5 minutes now.
Okay. Then this slide shows some conceptual design of our proposal. So inspired by this GJJ device, we propose a document detector which consists of a multitude of GJJ device. This A shows a single graphene strip, which is the assembly of long graphene strip and a number of superconducting material strip like this way. And then this each sequence of superconductor, graphene superconductor represent a single GJJ device. And then the full this figure B shows us full detector unit where all the GJJ devices are connected in series like this way. So even a single switched GJJ allows the series distance measured between the source and drain switched from 0 to find the value. So that's why we can say, oh, some signal is deposited in this detector like this way. And then the energy threshold can be controlled by the strip with this WJJ. With 3 micrometer width, we can achieve 0.1 millielectron volt energy threshold. With 10 times larger width, we can achieve 1 millielectron volt energy threshold, and so on. If we need a much larger scale detector, then this kind of much larger scale detector can be made of a stack of such a detector. This kind of 2D detector units. This is last part. To calculate experimental sensitivity, we should consider scattering between document traveling in 3-dimensional space and free electrons living in 3-dimensional. However, these free electrons are confined in 2-dimensional graphene layer. So the key point is the electron is still confined in 2D graphene even after the collision. So that means no significant momentum change along surface normal direction. We call this normal direction as a z-axis. And then I show some very short summary of calculation procedure. The first line is a kind of this part is a typical thing. The total expected event count per unit mass and unit time is given by this kind of relation. And then here the total event is given by this proportional to the target mass and runtime. And then this number of event proportional to spectrum cross-section between electron dark matter and dark matter flux and runtime and so on. And also this capital N sub E is total number of electrons within target. So actually, as I mentioned, our target is 2-dimensional graphene sheet. So we should convert 3-dimensional version to 2-dimensional version using this kind of relation between 3-dimensional to 2-dimensional. And then also we need 2-dimensional electron number density. So we the typically well-known one is three-dimensional version. So connecting two-dimensional and three-dimensional relation, we can calculate two-dimensional version of electron number density using this kind of three-dimensional momentum integral. Here, this part, the delta function for G component of moment transfer is constant with the assumption of no significant momentum change along surface normal direction, this graphene surface normal direction. And then in this calculation, we should include the Maxwell-Boltzmann Maxwell distribution. However, only the graphene surface parallel Dagomar velocity is relevant for our calculation. So we use that part in. So we take a prime projection of modified Maxwell-Boltzmann distribution in our calculation, and then event rate on surface in 2D material can be seen like this way. Here, as 2D means the surface structure function for two-dimensional system. So we try to find the relation between two-dimensional version of structure function to three-dimensional version of structure function, with this kind of step. And then we finally can get two-dimensional structure function using three-dimensional function with this delta function relation. And then within this structure function, Pauli blocking effect already encoded in this function. Okay, and then to find the final relation, by plugging all of this kind of equation and relation into this master equation, we get a final relation. So now we are in the position to study document signal sensitivity, which would be achieved by the proposed GJ detector. And then, running out of time. So this is our final result. So using this kind of relation, and then we can easily estimate our center of the limit. To get this kind of center of limit, we require larger than 3.6 event under the negligible background assumption. So as you can see from the two panel, the proposed detector can improve the minimum detectable document mass up to 0.1 kb. That means by more than 3 order of magnitude over the ongoing existing experiment. That means our experiment have capability of proving sub-kb document with great expected reach. So this is summary of my talk. To save my time, I did my last slide. The key point, I wanna say two key points. One is, one interesting point of our detector is our signal rate depends on document flow direction. So that means the angle, this one has angular dependence on document flow direction and graphene surface. And also now we are planning to do the first experiment with the existing GJ device sample. Thank you.
Thank you very much. Is there any questions or comment? David.
Hi. I was just wondering if with these kind of setups, you're also sensitive in some kind of sense to the direction of the dark matter, or is that doesn't make any sense?
What do you mean?
What I mean is that you're effectively constructing a two-dimensional layer where you're looking for WIMPs, right? So I would expect that is it or is it not that you're more sensitive in a particular direction when the WIMP is kind of crossing more?
Definitely. This is one of the key points. As I mentioned in my talk. Okay. So in our calculation to estimate event rate, the relevant part is here. This is, as I mentioned, okay. Graphene surface, surface parallel document values profile. So yeah, that means only the velocity, the parallel component of dark matter velocity is relevant to this energy transfer. So if dark matter is coming into the normal direction to graphene surface, the energy transfer is almost negligible. However, if they are coming into the graphene surface parallel direction, then energy transfer is the most efficient. So that means if some signal is observed within our detector, that means the signal should have some angular dependence. So that one is our checking point. If some event is observed within our detector, we can easily check that one is really induced by dark matter flow or not.
Thank you.
Okay, next question is from Hyunseok.
Maybe could you go back to the detection principle slide?
Okay. This one?
Yeah.
Okay.
So my question is that maybe it's just terminology, but in this case, this kind of device is categorized into the calorimetric detector.
Oh, okay. So not our purpose. The original device invented in condensed matter physics side, their final goal is a single photon detector. But as a first step, they check their detector working as a bolometer.
Bolometer.
Yeah.
Could you explain what is bolometer?
Because to be a single photon detector, that means really single photon. One single photon is really coming into the some device. Then each coming to photon can trigger some signal. Then we call it this is as a single photon detector.
Okay.
However, some like a bunch of photon or something like that can coming into the detector material, and then it can deposit some portion of energy. Then this kind of mechanism can be acting as a some kind of thermalization or thermal heating of the material. So the device can measure such a thing. Then it call it just bolometer.
Okay. Then I remember that there is a kind of called linear amplified detector for photon. Is it different with this bolometer and?
Actually, I'm very sorry. Yeah, actually, I'm a theorist. Yeah, even more, I'm a particle physicist, not quantum physicist.
Okay.
So probably that part is not my specialty. So if I say something, then it could be long statement. So that means to avoid something.
Then the single photon detector is qualitatively different with this kind of what do you explain? Or just sensitivity problem?
Not sensitivity problem. Yeah, because single detector means merely single something is coming into the detector. We can say if some detector working as a single detector, then if you measure something, then merely single something coming into the detector. However, if we haven't checked such a possibility, then such a thing can happen with a bunch of events or a bunch of energy devices, something like that. So
then it might be there is some qualitative difference with
something like that.
Okay.
But their proposed idea was originally single photon detector.
Okay.
Yeah.
Then my last point is that the main error from this device is coming from thermal noise.
Oh yeah. So okay. Then
is it right?
I'd better move quickly. Just a second. To save the time, I'll change very quickly. Back up slide. Okay, this one. And then just a second. I share my screen. Yeah, this is my backup slide. Yeah, actually, yeah, internal background is one of the crucial background for this kind of device. So it's quite crucial to keep the system temperature low enough to suppress potential thermal background or noise. So this experiment was originally done in up to 10 millikelvin temperature. With this temperature, expected the average of expected thermal noise is just at the level of micro milli electron volt energy. So that means even with higher tail energy, with this low temperature, this kind of thermal noise cannot trigger this GJJ junction.
Okay, thank you. Thank you very much.
Okay, for further question, we may use the discussion time. So let's thank the Chongchul again.
Okay, thank you.
And the next speaker is Valentina from IFIC. Valentina?
Yes.
Show your, yeah.
Hello, good morning.
Yeah.
Good afternoon. Can you hear me?
Yes.
Okay.
You may try to share your screen.
Yes, 1 second. Do you see it?
Yeah.
Okay. And if I go down, do you see the next slide?
Or you can use the full screen mode.
Okay. 1 moment. Okay, here.
Right.
Like this, better?
Yeah, yeah.
Okay.
Good. Okay, so Valentina will talk about new physics searches with neutrino experiments. Please.
Yeah, okay. Thanks a lot. Thanks for the opportunity of giving this talk. Indeed, I will focus mostly on neutrino physics in this talk, and I will discuss how we can search for new physics and new effects with the neutrino experiments. And this talk is mainly based on a couple of works which I've done recently. So this is the outline of the talk. I will start with a very brief introduction on neutrino physics, in particular on the current status of neutrino global fits. And then I will discuss 2 different topics. In the first part of the talk, I will discuss how we can probe neutrino quantum decoherence with reactor experiments. Whereas in the second part, I will discuss how we can search for new neutrino interactions with the coherent elastic neutrino nuclear scattering process. Okay, let's have a look at what's the current status of lepton mixing and neutrino physics. So as of today, data favor a 3-active neutrino oscillation framework, and most of neutrino oscillation parameters have been inferred by detecting neutrinos coming from the sun, the Earth's atmosphere, the nuclear reactors, and accelerator beams with quite good accuracy. So this table summarizes our current knowledge of neutrino oscillation parameters, and it has been extracted by the most recent global fit from the Valencia group. As I was saying, we have reached a quite good precision in most of these parameters. However, there remain some open questions. For instance, we still don't know what's the octant of the θ-3 angle, what's the ordering of neutrino masses, and what is the value of the delta CP phase. So current data suggests a slight preference for θ-3 to lie in the second octant, and the preference for the CP violating phase to be between pi and 2 pi. And also almost 3 sigma hints in favor of normal ordering, which actually goes above 3 sigma if combined with cosmology. However, there is an updating analysis in progress, and probably the inclusion of new data from Super K, T2K, and NOVA will probably affect some of these results concerning, for instance, the preference for normal ordering, the CP violating phase, and the θ-3 octant. Well, in general, anyway, our interpretation of neutrino oscillation experimental data rely on some assumptions, for instance, on the fact that we assume that there are no sterile neutrinos, and also that neutrinos only fill the weak standard model interactions, and they don't have new interactions. So if these assumptions change, our interpretation of neutrino oscillation data could also change. This is what I will discuss in this talk, in particular concerning two different topics. So the first one is actually a new effect, which is neutrino quantum decoherence, which would indeed affect the oscillation probability. And I will discuss now how we can probe this effect with the reactor experiments. So let me introduce what I mean with the neutrino quantum decoherence. So neutrino oscillations are an example of flavor oscillations, and they arise when the particles produced and detected in an experiment are superpositions of different mass eigenstates. So they are a consequence of the fact that the charge current weak interactions are not diagonal in the basis of the mass eigenstates for both the charged leptons and the neutrinos. So even though the existence of neutrino oscillations have been proven by many experiments, as we have just seen in the previous slides, the theoretical description of this phenomenon is actually still affected by some subtle points. In particular, the signature dependence of neutrino oscillations on the distance between the neutrino source and the detector cannot be observed unless the source and the detector are fully localized. So the quantum mechanics uncertainty principle implies that when neutrinos are produced at some source, they must be in a coherent superpositions of states of well-defined and different mass. So it turns out that coherence is really essential for neutrino oscillations, and a consistent derivation of the oscillation probability requires to use the wave packet formalism. Actually, to date, there is no experimental evidence of distance-dependent loss of coherence for propagating neutrinos, and this is the topic of this first part of the discussion. The physics that leads to this type of decoherence is the fact that the wave packets corresponding to different neutrino mass eigenstates will propagate with different speeds. So if one waits enough time, these wave packets ultimately can separate. Eventually, then the wave packets of two different mass eigenstates can have no significant overlap anymore, and therefore the coherence will be lost, thus leading to a suppression of neutrino oscillations. It turns out that nuclear reactors are actually excellent laboratories to study neutrino coherence. Indeed, the observation of decoherence effects in terrestrial experiments would require a long baseline, low neutrino energy, and a small wave packet width. So that's why we wanted to explore whether high resolution, high statistics measurements of the flux of electron antineutrinos produced in nuclear reactors could be sensitive to neutrino decoherence, or at least they could be used to place meaningful bounds on how coherent nuclear reactors are as neutrino sources. So at this scope, we consider three different experiments, two current ones, which are Reno and IABE, and the future one, which is Juno. So Juno in particular, we have a longer baseline compared to the previous two, and therefore it will also measure the solar parameters and atmospheric mass splitting with quite good precision. Let's have a look at how neutrino oscillation probabilities change when we include this decoherence effect. So the survival probability of electron antineutrinos produced in the nuclear reactors gets this form when we include the decoherence effects, which are encoded in these Xi parameters, which quantify the loss of coherence as a function of the neutrino energy and of the baseline. So the X's are actually defined in terms of some coherence lengths, which depends on the neutrino energy, on the square mass differences, and on this parameter sigma. So this sigma is practically the effective width of the neutrino wave packet, and it has dimensions of length. It will depend on the spatial delocalization of the neutrino source and of the detector. So to have a visual idea of how these decoherence effects affect the oscillation probability, we can have a look at this plot, which shows the survival probability for these electron antineutrinos as a function of the energy. This is for the Juno experiment. And the green curve is what we expect in the standard model case, which is equivalent to set the sigma, that is the wave packet width, equal to infinite. If we set a finite value of this sigma, a small one, as you see, of the order of 10 to minus 3 or 10 to minus 4 nanometers, these oscillation probabilities will change, and we see that it will become the black or the red curves. In particular, the fast oscillations are those that will disappear first, and also the effect will be more pronounced at small neutrino energies. So you see already from this picture that indeed we expect this effect to be visible at Juno. So as I was saying, we consider 3 different experiments. So let's see how what's the result of our analysis in terms of trying to ruling out these decoherence effects. So the first plot shows the result of the analysis for 2 current experiments, Reno and Diabay, in terms of current of oscillation parameters, θ13 and the square mass difference 3.1 versus the sigma, which is the width of the neutrino wave packet. So we see that when we allow for sigma to get finite values, we get a reduction of sensitivity for the standard oscillation parameters, and this is due to some correlations that appear between these standard parameters and the wave packet width. So in particular, small values of sigma are correlated with large values of the mixing angles or small values of the mass splitting. In the case of Juno, instead, this plot shows the future sensitivities for Juno. We get that the measurement of the standard neutrino oscillation parameters will remain mostly unaffected, even when we allow for the possibility that sigma is finite. Okay, also, so these experiments, these reactor experiments can actually set a lower bound on the magnitude of this neutrino wave packet width. So from the combined analysis of Reno and Diabay, we obtain a lower bound of the order of 10 to minus 4 nanometers. And we get this, that these bounds will be improved by a factor of around 20 in the case of Juno. On the other hand, if the coherence is really present in the data, we obtain that Juno will be able to exclude the no decoherence hypothesis at more than 10 sigma. So to summarize this first part of the talk, well, we were interested in see whether reactor antineutrinos experiments could probe these neutrino quantum decoherence effects, because up to now this position-dependent loss of coherence has never been observed. We have found that current reactor data from Diabay and Reno constrain the neutrino wave packet width to be larger than 10 to minus 4 nanometers, whereas the future data from Juno will improve this bound by a factor of 20. To get an idea of what these results mean, so as I was saying, we are setting a bound on sigma in nanometers. So when sigma goes to infinite, we basically have no decoherence effects, so we recover the standard model case. Juno will be sensitive to neutrino wave packet width smaller than, let's say, 2 in 10 to minus 3 nanometers. The current results from Reno and Diabay lie here around the 10 to minus 4. And now the question is what's actually the value of this neutrino wave packet width. So there are actually many theoretical estimates, and this is still not clear. So it depends on to which scale this width is associated to. So for instance, if we expect that this is associated to the interatomic spacing that characterizes the fuel inside the nuclear reactor, we would expect this sigma to be of the order of 0.1 or 1 nanometer. So this would be far beyond the reach of Juno. But on the other hand, if this width is instead associated, for instance, to the size of inverse beta decay nuclei, then this would lie here at 10 to minus 5 nanometers, let's say, and therefore it could be reached by Juno. In any case, so an eventual discovery of non-trivial decoherence effects in Juno would be very interesting, because it would indicate that our understanding of the coherence of neutrino source is possibly incomplete. Okay, then I would like now to discuss a different topic, which is also related to the fact that the presence of new physics could actually affect our interpretation of neutrino oscillation data. And I would like to discuss how we could probe the so-called neutrino generalized interactions using the coherent elastic neutrino nuclear scattering process. Probably all of you have heard about the observation of this process by the Coherent experiment in 2017. And it was a very interesting result because this process had eluded the detection for more than 40 years. Let me introduce what this process is. So the coherent elastic neutrino nuclear scattering is a neutral current process in which a neutrino scatters off a nucleus via the exchange of a Z boson. So this process was actually first proposed in the wake of the discovery of weak interactions in the neutrino sector. But as I was saying, it was not observed for many, many years. For this process to occur, the neutrino energy has to be such that the nucleon amplitude sum up coherently. So there is an upper limit, let's say, on the value of the incoming energy, of the energy of the incoming neutrino, which is of around 100 MeV. This leads to an enhancement of the cross-section, which indeed scales with the number of neutrons squared. And eventually this cross-section can be few orders of magnitude larger than the inverse beta decay process, which was first used to observe neutrinos. In the standard model, the cross-section for this process is well calculable, and it gets this form when we neglect the axial contributions. So this is a differential cross-section in terms of recoil energies. So we see that it depends on the mass of the nucleus, on the energy of the incoming neutrino, and on this QW, which is the standard model charge, which encodes the typical n-squared dependence. So this typical dependence is shown in this plot here, and which also shows where the current experimental results lie. So this process has been observed first using nuclei of cesium and iodine, so the results lie here, and then also more recently using nuclei of argon. But there is a plan by the Coherent collaboration to use also different targets like germanium and sodium to fully explore this dependence. This other plot instead shows the magnitude of the seventh cross-section in black versus, for instance, the inverse beta decay in red. And so it shows that indeed this cross-section can be actually quite larger. So despite this, while seventh is an exceptionally challenging process to observe, and this is because of the very tiny recoil energies. So it's true that heavier nuclei lead to higher cross-sections, but also to a lower recoil. So it's very hard experimentally to detect it. But the improvements, especially in the sector of dark matter direct detection, has allowed to reach this result. And indeed, this process shares many things with the dark matter direct detection. One is the detector technology, and the second one is the fact that sevens from natural neutrinos from the sun and the atmosphere will actually create the ultimate background for direct dark matter search experiments, giving rise to the so-called neutrino floor, which is usually shown in these direct detection plots. And so it turns out that it's very important to fully understand this process because we want to know where this neutrino floor exactly lie, and if, well, for instance, the presence of additional neutrino interactions could change this neutrino floor, and therefore our interpretation also of dark matter direct detection searches. Okay, as I was saying, so the first observation ever of this process was made by the Coherent experiment in 2017. This experiment uses neutrinos from PIDARs from the Spallation neutron source in the US. And the first observation was made using nuclei of cesium and iodine, and only 14.6 kilograms. So this is very interesting because it's one of the smallest neutrino experiments in the world. Then they recently repeated the observation also using nuclei of argon. But for our analysis here, we used the first result from 2017. The observation of sevens indeed opened the window to a very rich neutrino physics program, not only concerning fundamental neutrino physics, but also, for instance, supernova physics and the search for new physics like non-standard neutrino interactions, derived neutrinos, and so on. This plot shows the data points from a coherent experiment with their error bars, and the black histogram is what we would expect in the standard model. So we see that because of the still large error bars, we can have open room for new physics. So this result was used right away, for instance, to probe the neutrino NSI, the so-called non-standard interactions, which are usually parameterized in a model-independent phenomenological way via dimension 6 for fermion operators. So via this effective Lagrangian, where this NSI parameter epsilon gives the magnitude of the new interaction in terms of G Fermi. So this plot shows how the sevens process would constrain these NSI parameters, the orange and red bands, for instance, compared to other experiments like the CHARM, which is deep inelastic scattering. The constraints from sevens are particularly relevant in the case of which these new interactions are mediated by light particles, also because they would give rise to some nice features, experimental features, like it is shown here, where we see that in this differential rate we get a dip because basically the new interaction contribution is canceling the standard model one.
4 minutes,
okay. Yes.
You have 5 minutes.
Okay, thanks. So we wanted to to try to constrain new physics interactions and to enlarge the set, because the NSI are actually only a subset of a larger set of neutrino quark interactions that we call the neutrino generalized interactions, NGI. So now the effective Lagrangian has this form, and now the gamma can actually get all possible Lorentz forms from scalar to tensor, not only the vector one. And we wanted to constrain all dominant spin independent contributions, which are designed by the blue effective coefficients. So, well, the differential cross-section, it looks like this at the nuclear level. So these X's are the parameters that refer to the new nuclear currents, the scalar, vector, and tensor at the nuclear level. Then these can be related to the fundamental parameters at the quark level. We performed analysis for two scenarios. In the first case, we turn on only one new interaction at a time. In the second case, we switch on two interactions at the same time. So we performed the chi-square analysis comparing to the coherent data from 2017, and we get these results. So concerning the parameters at the nuclear level, we get these 90 and 99% confidence level ranges. And then, as I was saying, this can be translated into the fundamental parameters at the quark level, which are shown in these plots for the vector, the scalar, and the tensor interaction. And you see that we get some constraints in this parameter space, which are very similar to what is obtained for the NSI case. And we get that the scalar interactions turns out to be the most constrained one. In the second scenario, we allow for two interactions to be present at the same time. So our constraints in this parameter space change a little bit. Now we are showing them in terms of scalar and vector, scalar and vector and tensor interactions. And basically, well, the main result is that the presence of an additional interaction relaxes the bounds on the fundamental neutrino quark couplings. To see this a bit more better, we can have a look at this reduced chi-square in terms of XCV. The XCV is the new parameter that that is referred to the new interaction in the new vector interaction. So the red curve refers to the case where we have only the new vector interaction, of course, always on top of the standard model case. So when this XCV is more or less equal to -1, the chi-square is really bad, because what happens is that we are canceling the standard model contribution and we are getting basically zero events. But if we also turn on an extra tensor or scalar contribution, this will produce new events, and therefore the chi-square improves again. Okay, then to summarize the second part, we wanted to see whether we could use the recent coherent data on this seventh process to probe a generic set of effective Lorentz invariant non-derivative neutrino quark interactions. And we have performed two kinds of analysis. In the first case, we have seen that the scalar interactions are the most constrained when we turn on only one interaction. In the two parameters case, instead, we have found that the presence of an additional interaction relaxes the bounds on these fundamental neutrino quark couplings. So, well, this exercise was meant to show that indeed seventh offers a plethora of physics opportunities, and hopefully with more forthcoming data, both from coherent and also from other seventh experiments, mainly using reactors, will possibly allow to unravel the presence of new physics, and therefore to shed more light on the neutrino physics sector. And well, that's it. Thanks a lot for your attention.
Thank you very much, Valentina. So any questions or comments? You can freely.
Yes. Sorry, I have a question.
Yeah.
Yes.
Thanks for this interesting talk. In the first part, if I understood you correctly, you were referring in principle to the standard model with its neutrinos and quantum mechanics. There was no ingredients of neophysics, just that the consequences of quantum mechanics are not yet fully understood, correct?
Correct, yeah.
So imagine we would measure this wave package, the extension of the wave package. What would this tell us about our understanding of quantum mechanics? Or what would we really learn from this? I find it fascinating. I thought this must all be known, but you tell me it's not known. Yeah, so this was new to me, and I would like to,
yeah, actually, also for me, before starting this work, it was something new, and I was also surprised, and that's why I found this work particularly interesting. And well, I think there is still a lot that we should learn. So, well, I don't know. First of all, we would learn that indeed we don't know so well quantum mechanics, so we should probably investigate more. So for sure. Yeah, I mean, this is the main message. I would say that yeah, I mean, it's not a new physics effect. Is as you said, it's just quantum mechanics. So it's something within the standard model, but it can be there, right? So it's something that is worth trying to explore more and understand better.
Oh. Thank you. I really learned something.
I also had one question. This is Thomas from Korea. This is concerning the propagation of the neutrinos, because in principle you have propagation in matter, and this could affect this affects the oscillations. This could, in principle, also affect the decoherence. Do those propagation effects in matter play any role for the distances you are considering, and if so, is this taken into account? And is this easy, or do you really have to look for differences in decoherence and oscillation effects?
Yeah, so we did not take it into account, and yeah, probably would not be so easy to include it. So we assume that it would not play let's say, a relevant role in this specific analysis. Also, there are, for instance, some other works related to this, which assume, so we focused on the decoherence effects in the propagation, but you could also have decoherence in detection or in the production. And there is, for instance, a work from the Diabay collaboration on this. So, yeah, but in our work, we did not consider the matter effects.
I see. And do they play a role generically for reactor neutrinos, or are they more relevant only on longer distance scales?
I would say it's more for longer distance scales, but yeah.
Thank you.
Related to the previous questions, so if we assume that quantum mechanics is well established, then what kind of new physics disturb the coherence? Can disturb the coherence of the neutrino from the source and from the propagation.
Sorry, could you repeat that? I lost.
So what kind of new physics can disturb the coherence of neutrino from the source and the propagation?
Yes, for instance, well, there are some works on the fact that there can be an interaction of the neutrino system with a quantum environment. I cannot tell you much more of this, but so there is some quantum origin of new physics related to some quantum environments, which could affect this. But what we studied was just pure standard model physics, pure quantum mechanics. So with no new physics, no new effects.
Okay, thank you.
So the last question is from David.
Hi, Valentina. This is probably something very short, but in your slide 22, when you were showing that I don't know if it was an interference effect or that you're showing on the right plot, or is it in the form facts? Is it an interference with a kind of vector mediator, or what is that?
Yeah. It was exactly with a light vector mediator.
And does it happen for all? I mean, I suppose that this only happens for one isotope, or I was wondering how observable this effect was when you take into account the whole,
I mean, this is of course, this is theoretical first of all. So, well, experimentally, you don't see a nice dip ever. It's so this is the first thing, and then of course it depends a lot on the isotope. So if you use different isotopes, you could maybe probe these, or depending on the isotope, you would expect this dip to be at different recoil energies, right? Also, depending on the material that you use for the target. I mean, some materials are not pure isotope, but they are a mixture of several. So you would not see an exact dip, but you would see a depletion, but with the width.
So
you can
exactly.
Compute that.
That's also why I was wondering if there was any clever choice of materials that you could do to test this kind of effects. Because I suppose that this would also give you a handle on how to discriminate possible new physics.
Ideally, if you could use materials that have the most different Z and A values, it's actually a combination of the two. So I don't remember exactly if it's like the sum or it's a ratio of the sum over the Z minus A or the opposite, but you can choose your isotopes to identify this feature at its best.
Thank you.
Okay, thanks a lot, Valentina, again.
Thank you.
So our last speaker is Andrew from UC Leuven. Andrew?
Hey, I'm just trying to share my screen. Can you see it?
Okay.
Yeah.
So Andrew, talk about your insights into dark matter from EFT basics.
Yeah, I just is it moving? Does it move? Just make sure. Yeah. Can everyone hear me okay? I'd like, because this is a new microphone. No? Okay. Well,
yes, all good.
Okay, thank you very much. Okay. If you followed along the slides via the link on the Indigo, this is really for full screen, but you can always go zoom in or zoom out. But yeah, so let's get into it. Right, so first of all, my name is Andrew Cheek from UC Louvain in Belgium. And firstly, I'd like to thank the organizers for inviting me to talk and also for producing such a nice event. You know, I've particularly enjoyed listening to talks that are a little outside my comfort zone. And, you know, in a way, this paper that I'm going to talk about today is kind of fitting in that sense, because really it's me and Chiara Arena who got together with two EFT experts, and then we you know, figured out, we noticed that there's still some things to be learned by the dark matter community about dark matter, possible dark matter solutions from simply the basics of effective field theory. So that's what I'm going to talk about today. So first of all, you know, let's think about dark matter interacting with light. This is what we are interested in. Everything we know about dark matter says that it's electromagnetically neutral, or at most milli-charged. At the same time, photons are a primary messenger of astrophysical and cosmological probes, which perhaps seems a little bit worrying, but you know, it's fine because standard model particles hadronize and everything like that, so they emit and they radiate and they emit photons, as well as other particles that we can pick up in astrophysical searches. Also we can think about, you know, generically BSM scenarios with heavy charged particles will couple dark matter to photon via loops. These new charged particles, if they exist, are too heavy so far to be seen directly at the LHC. So maybe an effective dark matter photon interaction can give us some insight in the possibilities and the standing and the situation of you know, the experimental landscape at the moment. So let's just have a look at the operators we consider, the effective operators we consider. We consider as dimension 5 and dimension 6, which only leave us with coupling a photon to a fermionic singlet, which is going to be our dark matter. So that leaves us with only 4 possible interactions. Okay, so we have the magnetic and electric dipoles here at dimension 5, and at dimension 6 we have the charge radius and the Majorana and the anapole dark matter, which, as you can tell, probably you can infer, is that for a Majorana fermion, all of those 4 couplings are 0 except for the anapole dark matter. It's also interesting to note that the anapole is velocity suppressed in its annihilation cross-section, which is interesting because it allows you to firmly produce dark matter in the early universe and evade these kind of stringent bounds from indirect detection in later times. And here I show, you know, the relic density line for the Dirac case. And I show how the different experiments are really starting to be very constraining on the freeze out picture below 10 GeV. Whereas this line isn't here for the Majorana case. So, you know, I was kind of interested in, okay, let's take the hardest thing to constrain and let's see what we can say about it, especially for light dark matter, like in this region. Right, so before I go any further, I just want to recap EFTs a little bit. So effective field theories are incredibly useful. People have been using effective sort of pictures of high energy physics all week. So I don't need to convince people of anything there. And I like them because it sort of helps you focus on the relevant degrees of freedom and the things that you can actually see in the processes that you're studying. You know, here's the classic textbook picture of the Fermi effective theory. Also, they provide for high energy physics, they provide a systematic prescription for searching for and constraining new physics. You build your operators at higher dimensions, and each dimension you introduce a mass suppression, and that suppression is the scale of approximately the scale of the new physics, and that suppression allows you to go systematically from one extra dimension to another. And in principle, if the new physics is heavy, then in principle this is like your calculations get more precise the higher you go, much like perturbation theory, So something you should always keep in mind is that when you're building your higher dimensional operators, you use the symmetries of the low energy theory. For example, in SMEFT, you use the standard model gauge symmetries, and in direct dark matter detection experiments, you use Galilean symmetries. So earlier I showed the couplings to the photon that we have, the effective couplings to the photon. But then in the recap of effective field theories, I said that in SMEFT you should use the standard model gauge symmetries or standard model symmetries, and then you might say, well, the electromagnetic field strength tensor isn't isn't invariant under the standard model gauge group. So this is perhaps a problem, right? But in direct detection experiments where these operators are usually studied, it's okay because there's this relation between the two, and at low energies, the two are essentially equivalent, okay, up to some Cos-Weinberg. So through the history of considering these effective operators, it was often kind of considered a choice. It's something, maybe we can do this if you wanted to, but really I'm here to show you that it's not a choice, and it has deep implications in the phenomenology, which is kind of interesting. Okay, so before I go anywhere before I go into the paper more, I just want to do a little bit of a history of these operators, okay, just so we can get an idea of where they came about, when people have been considering them, and maybe we can understand why people kind of made a few mistakes along the way. So Postoulos and Veldes in 2000 had a paper where they focus on these electromagnetic form factors. I think they only had the dimension 5 ones, and they only focus on direct detection. So fine so far. And then later, a couple of years later, some people in 2004 had a very comprehensive study of the dark matter phenomenology, including relic density calculations with these diagrams happening in the early universe and setting the relic density of dark matter. And they compared lots of experiments and saw what the landscape was like in 2004, a long time ago now. And they had masses of the dark matter going up to 10 to the 4 GeV, which, perhaps rings alarm bells already. So then Ho and Scherer in 2012 introduced the Yanopole dark matter, and they were hesitant to consider the mass above the mass of the dark matter above the weak boson mass. And we assume that's because they kind of knew that they'd have to take some extra care when you go to that scale. Okay, so now let's fast forward, 10 years almost, to last year. And we have two recent works which kind of put me onto this subject. And one, which is really exciting, was by Flores et al. And appeared in PRD, where they studied the VBF signature coming from the triple vertex between two W's and a photon here. And then it gives, through the effective vertex, it can go into your dark matter. Okay, so using specific VBF topology, they were able to get very impressive results, which was really cool. I was super interested by it because, like I said earlier, the Yanopole is one of the harder moments to constrain. But also, so just now I showed you these diagrams, for annihilation, for dark matter annihilation, which which were used in 2004 for the calculation of the relic density. But this diagram here suggests we should have another diagram included. Okay. Also in 2019 in JHEP, we have Bradley Kavanagh et al. Asserting that the interactions are subdominant. These interactions here are subdominant compared to the photon operator, specifically in direct and indirect dark matter searches. Okay, so this is quite interesting because here we have a really good result in colliders, which relies on kind of this interaction inside. So I wanted to, it seems like these two are a little bit in conflict. So I wanted to, see what's going on here. Okay. And, so the first question was, can we ignore the chi-chi goes to W plus W minus? Let's take the anapole because that's where the VBF signals were promising. Okay. And we get the amplitude square and we take some limit where the center of mass energy squared is much greater than the masses, except for the cutoff scale. And then we get this, okay? We notice here that, so this is the highest order of S. So we notice here that the amplitude grows as S to the 4. Okay, so this is already a bad sign. Okay, because at most, for a dimension 6 effective interaction, it should be S to the 2, right? And that's because 2 to 2 amplitudes are dimensionless, and the only scales present at high energies are lambda and S, meaning that it should yield something like the amplitude should yield something like S to the lambda squared, and then when you square it, you get S squared. Also, you might notice that it's not a clean high energy limit. For example, if I set the mass of the W to 0, then it blows up. So yeah, I mean, this looks a bit sick. You could say that, okay, well, but for the important cosmological calculations like the freeze out and the relic density calculation, S is really proportional. It's very close to, it's kind of close to the mass of the dark matter squared. So it's in non-relativistic. Does this kind of thing still happen? And I show here for different values of mass, as soon as the dark matter mass can go into W's, it starts to blow up and win dramatically. Okay. So you can also do it, you can show quantitatively why this interaction or why this amplitude is sick and why this model is sick by seeing where unitarity violation happens using partial wave analysis. And then you can also, and you can also, but that's something that usually happens in EFTs. But something's weird is when your unitarity is violated below the cutoff scale. So that tells you your theory is sick, not just because you're using an EFT, okay, which is, and this is the constraint here. Right, so I mean, yeah, some of you might be going, yeah, we get it. It's bad to use the wrong thing, but we all know why it's wrong. Okay, so why don't we see what happens with the solution we already know, okay? And instead of using the electromagnetic field strength tensor, we use the hypercharged field strength tensor. Okay, and then here you go, you have a Z in this diagram, which cancels the S to 4 growth, and then you get a nice clean high energy limit. And as we expected, you get a S squared growth at the highest order, which is great, okay? And you see here in this diagram, or this plot, sorry, that we have tamed the behavior of the chi-chi goes to W plus W minus, and although it's there, it's substantially smaller. This is a log scale. It's substantially smaller than the dominant channels. Okay, so is Bradley et al. Correct, and can we just ignore these W and Z bosons? And already you can see one reason in this plot why you can't, and that's because in order to fix the high energy behavior of W plus W minus, we had to include the Z, okay, and then there's lots of lower energy contributions or phenomenology that the Z gives you, okay. So we have the Z resonance or the Z funnel here. We also have the Z width and the measurements of invisible Z width. And also now because we have Z, we have neutrino interactions. And if we look, this is in this plot in the yellow. In yellow, we have neutrino interactions, okay? And we see here that it's actually not, not that far off the dominant channel. So I mean, maybe there's some interesting physics there. This picture right here isn't actually the anapole, it's the charge radius, but they're very similar, and this is the one I had at hand. Right, so let's go back to the promising VBF signal, which got me interested in the first place. And now we don't just have the photon, we have the sort of interference with the Z in this diagram, and as you can imagine, like in the annihilation case, it cancels out, right? So then the Flores people, Flores et al. Were able to get a slightly better line. We replicated their VBF search. They got a slightly better line than we were able to replicate. But basically the point of this plot is to show that the black solid line, which is considering the gauge invariant hypercharge field strength tensor interactions, you get almost an order of magnitude sort of worse in terms of your collider sensitivity from the VBF signatures, which is kind of disappointing. I'm going to be honest. Yeah, so it meant we had to go back to the monojet plus missing transverse energy, which is now probably the best signal. Right, so so we took the most recent CMS analysis of the monojet plus missing energy, and we calculated the bounds for each of these operators, and we can see here that for the dimension 6, we're getting to a constraint around a TeV, and then the orange and green lines are projections for high luminosity with different values of systematics. I'll just zoom in a little bit. Maybe that can be a bit better. Right. So yeah. So I mean, you can see here that the dimension 5 operators here improve substantially over the dimension 6, and this is basically because the dimension 6 grow more with energy. The distributions grow more with energy. So the new physics contribution in the search populates the high energy bins more, which have lower levels of systematic uncertainty, and in the dimension 5 interactions, that's not the case. So they're quite affected by systematic uncertainty. Okay, you might think, okay, so those are results. You just ran it through the EFT machine, and you got some results. But you have to be careful of EFT validity, and that's something in the paper we take care of. I don't have that much time to talk about it now, but we have to make sure our process is sufficiently below the cutoff, and you can do a naive kind of approximation, which requires that your cutoff is greater than the highest energy bin that you consider in the experiment, and you can get these kind of, depending on if you're considering dimension 5 or dimension 6, you can get these relations, which basically tell you, okay, for a Wilson coefficient above the ratio of the max bin considered in the thing and the limit, REFT probably makes sense. Okay, and for the limits I just showed, roughly our Wilson coefficient above around 1 is it says that the EFT is kind of sensible, but yeah, we look into this a bit more, and yeah, so it depends. Then you have to go into UV physics and what models you want to consider. Okay, so then let's go to the astroparticle constraints. So a customary first calculation for any dark matter study is to check whether it was ever in thermal equilibrium and what happens with freeze out. We were no different, and on the right here we show the lines, solid and dot dashed, to be the difference between considering the hypercharge and the electromagnetic field strength tensors. This is dimension 6, this is dimension 5, and also the gray regions are showing the area of which naive perturbative unitarity doesn't work. Okay, here we've got dotted, basically because you might have noticed, we've got dotted and solid gray. You might have noticed earlier that I had a dimension 5 interaction with a double insertion with 2 of the effective vertices. Usually you don't see this that much in EFTs, basically because usually when you go up to a higher dimension in the diagram, you can usually redefine that diagram in some way by dimension 6 or the higher dimension effective operators, but that's not the case for us, so we consider it. And really the dimension 5 interactions should be considered as dimension 6, so that's why this unitarity limit changes. So here's where the relic density lines lie. Cool, and then we go ahead and we perform up-to-date indirect detection limits, and we show 3 plots here, basically because like I said, the anapole is kind of not constrained by this. But we have the charge radius, the dimension 6 operator, and the magnetic and the electric dipoles here. Also, the electric dipole is velocity suppressed, so you don't get it in indirect detection experiments. However, like you don't get the S channel process. However, the T and U channel processes aren't velocity suppressed, so that's where you get 2 dark matter going into 2 lines of photons. So we still have constraints there. And so yeah, the main difference between previous studies is that now we have to consider what could the neutrino experiments constrain and what could future neutrino experiments constrain, because now we have that channel. Okay, and you see here maybe they're not doing so great in compared to Fermi, but in the future, with KM3net and others, perhaps there's something that can happen. And the fact that they're competitive is cool because you can have some kind of complementarity between the searches. So here on the left, we're very kind of comprehensive with all the lines. In the middle, we kind of just go with the most constraining. Yeah. Okay, so now
3 minutes.
3 minutes. Okay, thanks. So we also, in the paper, if you're interested, you can have a look. We also do the direct detection limits, but like I said at the beginning, it doesn't really change the situation much. But when you put everything globally, it's quite interesting. For dimension 5, this is kind of known already. That direct detection, sorry, really strongly constrains the whole relic density line area. And here also we have the constraint from the invisible width. And because I have a little bit of time, I won't concentrate on this. And dimension 6 things are a bit more complementarity between different types of searches, and we've got a little space left for the thermal relic to be a viable solution. But if you think about whether you want this to come from loops, you also have to incorporate the loop factor, which then gives you less promising kind of look at the situation. So maybe relic density doesn't come from the sort of thermal freeze out, which is perfectly possible. And we see on the antipole case in particular, the one that I am most interested in, we see this great complementarity between direct detection and colliders. Okay, but also what's interesting is this Z decay width, the invisible Z decay. It's way better in the low dark matter mass than future. Oh yes, I should have said, sorry. These direct detection bounds are coming from xenon 1 ton here. This is LZ projection. This is super CDMS projection. And you can see here that the Z decay width is way stronger than the super CDMS limits for the coupling to the hypercharge, right? And then so if I take some results from the electronic recoil experiments like xenon 1 ton and xenon 10 and go even further in the low mass, I can show, we can see that this has kind of big implications for what kind of signal, or whether we can sort of feasibly expect to have an antipole dark matter in the near future from these experiments. And it doesn't look like that's the case. And I thought that's kind of interesting because we're at the, we go to the high energy to show how this theory is sick, and it tells you something about even the low energy processes in direct detection experiments and the low mass. And you can try and get around this constraint if you want, but you have to fix unitarity violation before with this relation. And if you plug the numbers in for this constraint around, what is it, like 10 GeV, you get, I think it's 120 GeV. So that's probable by the LHC. You need to fix it before then. Okay, so this is my last slide. So hopefully I've convinced you that there isn't really a choice between B and F, the hypercharge and the electromagnetic. And sadly, it means that the promising VBF results are no longer promising, but there are other phenomenological constraints opened up. And, freeze-out scenario is still possible in dimension 6 interactions. And like dark matter experimental collaboration should be aware of these constraints of Z width, because they do projections now for the constraints of the antipole, for example, and they're not aware of this. Okay, so yeah, I guess I'll do this and say thank you.
Okay, thank you very much, Andrew. So any questions or comments? You can just stare without raising your hand.
I have a question concerning the first part that you were showing, the calculation of E plus or minus going to a photon, and then, so how was it? Sorry. Can you show the diagram again where you included the effect?
So I think it's probably somewhere here.
One more, at least.
Okay.
Yeah. Okay, exactly this one. Yeah. So, and if I understood you correctly, when you look only at the exchange with a photon, then you get this result that has the wrong high energy behavior with the S to the 4. Yeah. Which is of course not acceptable. But then when you include also the Z boson, etc., this is kind of cures the situation. Did I understand this correctly?
Yeah, exactly.
Isn't this exactly the same situation when you look at WW to WW, where you not only have to include the photon and the Z, but in the end also the Higgs? And I would guess if you would, it's the same kind of effect that you see here, or not?
Yeah, I think so. I mean, and this is why the title of the talk is kind of learning new things from the basics of VFTs, because this is really just, remembering that, oh yeah, our EFT should really be standard model.
And I guess the operator that you insert there for the photon dark matter interaction automatically also gives you a contribution to the Z dark matter interaction, correct? You can't say you have only the photon or only the Z, because in the standard model, I mean, they come from the same origin. Yeah, they are a mixture of two other states. So you can't get one without the other. So it would even be unnatural to leave the other part out.
Yeah, yeah. And so, I mean, the reason why we took so much care in this is because we noticed that recently these separate papers or papers were coming out still treating these interactions as if it was okay. And really, we wanted to really kind of stress the idea, and I think this can happen with kind of different or divergent kind of sub-communities in the field. You have the EFT people who, really have this as second nature, and dark matter phenomenologists who might, know it's true but forget to use it every day.
Okay. Thanks.
Thanks.
I have a question concerning the EFT use here. So if you take a model and build an EFT from it, and EFT should be valid as long as you don't hit additional resonances, particles, and as long as you don't get unitarity violation. And here in this example, something goes wrong as soon as you go to a relevant mass scale above the W or Z mass.
Yep.
Right? And what matters here is the momentum transfer. So this is completely what you would expect, that a theory
exactly
have only photons is valid up to a scale where you start to see effects of electroweak gauge bosons and the Higgs, basically.
Yes, but it's
more, or
but because we want to stress the fact that we are able to go, in some experiments, we are able to go above the electroweak sort of bosons, okay, and
yes,
and that has implications for low energy dark matter searches, okay, because you have to fix this photon interactions by the time you get to the LHC. And then we have the solution already, and that's the standard model. And then so by using the standard model instead of the electromagnetic field strength tensor, you then get a constraint from the invisible Z decay, which in the example of the anapole dark matter for very light dark matter masses, and with processes way below the electroweak scale, you have a constraint which is huge compared to the best experiments in that region.
I see. So you're basically saying if I take results at very low energy for an EFT and I want to compare this to higher energy bounds from LHC, for example, I have to match the EFT at the low energy with the EFT I can apply, or with the full standard model even, I can apply at the high energy in order to consistently extract my constraints.
Yeah, it's all about getting this global picture of where we are with these
okay.
Yeah.
Thank you.
Thanks.
So no further question? Okay, then let's thank Andrew again. So this session is over now, and we will have a 10 minutes break. So
yes, let's reconvene at 10:30. Yeah?
Yeah, okay. And 5:30 in Korean time.
Right, sorry.
Yeah. Let's see, 10:30 or 5:30.
Very good, yes. I would like the two speakers of the, okay, good. Okay, let's start with the last part of the fifth IBS-IFT-MultiDark workshop. We have two more talks on phenomenology. And we start with Iñaki Lara, who is right now at Warsaw University, and he will talk about the Gravitino, muon G-2, and long-lived particle searches at the LHC, everything together. Please go ahead, 25 minutes.
Okay, thank you, Sven. Thank you for the invitation, and good morning and good afternoon. As I said, as Sven has said, I'm going to talk a bit about all of these things, more about long-lived particle searches. The words included in these slides are made in the context of the mu-nu SSM. The mu-nu SSM is a supersymmetric model that extends the MSSM content with right-handed neutrino superfields. These superfields are coupled to the Higgs superfields to solve the mu problem of the MSSM, and also couples to the left-handed lepton superfields to give mass to the neutrino sector. The consequence of these couplings, the neutrino-Yukawa coupling and the lambda coupling being at the same time in the superpotential, is that their parity is not a symmetry of the model. As an example, through this lambda coupling, a Higgsino could decay to standard model Higgs right-handed neutrino. Of course, if R parity is not there, the LSP is not stable, and the lightest neutral fermion cannot be interpreted as dark matter. However, under some circumstances, the gravitino could come as an answer for this and be a viable dark matter candidate. So one particularity of this model also, apart of having R parity explicitly broken from the superpotential, is that if you take the limit of vanishing neutrino-Yukawa coupling, you restore R parity, because then you can reinterpret these singlet superfields as the right-handed neutrino superfields as singlet superfields, as in NMSSM, and R parity is again a symmetry of the model. So all through the model, when you take the limit of vanishing neutrino-Yukawa coupling, you take the limit of R parity being again a symmetry of the model. So after electroweak symmetry breaking, all the neutral scalars can develop vacuum expectation values. Particularly, the leftest neutrinos can get BEVs, because now R parity is not protecting this, but with a difference. Since in the limit of vanishing neutrino-Yukawa couplings, these neutrinos should get a zero vacuum expectation value. In this limit, these neutrinos go to zero. Therefore, for example, for the rightest neutrinos, we expect the BEV to be of the order of the SUSY scale, but the leftest neutrino BEV is going to be smaller in comparison. So after electroweak symmetry breaking, the BEVs of the scalars generate several effective terms. In particular, they generate an effective mu term through the lambda coupling and effective Majorana mass for right-handed neutrinos and a Dirac mass for the neutrinos. With all of these together, if one chooses a neutrino-Yukawa coupling of the order of 10 to the minus 6, with the particles of the spectrum being in the SUSY scale, one is able to reproduce the correct neutrino physics. So since R parity is broken, in this model, all the particles with same spin, CP, and charge properties mix together, because the R parity is not separating particles in different blocks. In particular, all the neutral fermions mix together, Gauginos, Higgsino, right-handed neutrinos, and left-handed neutrinos, and mix together in a mass matrix that has a generalized seesaw structure. The block that is capital M has entries which are all proportional to M SUSY. It has the Gaugino masses, the effective mu term, the Majorana masses of right-handed neutrinos, while the diagonal blocks are smaller in comparison. It takes this limit of small neutrino-Yukawa couplings. Assuming this hierarchy between the capital M and small m, one can make a three-level approximation for the effective mass of neutrinos. One can separate two cases. The one with one generation only of right-handed neutrinos is able to get a three-level only masses for one generation of neutrinos, but including the three families of right-handed neutrinos is able to give masses of all of them. And with one particular result, that is that even if neutrino-Yukawa couplings are diagonal, the effective mass has the diagonal terms needed to reproduce the correct mixing angles for neutrinos. This expression that is a bit lengthy, it can be separated in three blocks. The first part is the contribution to the neutrino masses coming from the mixing of left-handed neutrinos with right-handed neutrinos, and is suppressed here in the denominator by the Majorana mass of right-handed neutrinos. This other term in the middle came from the mixing of left-handed neutrinos with Gauginos and is suppressed by Gaugino mass. And the third part came from the mixing with the Higgsinos. So let me talk a little bit about dark matter, even if it's not the main topic of the talk. So since it's a supersymmetric model, there is also a gravitino in the model. The gravitino has an interaction term with the photon field strength and the photino. In our parity conserving models, this means that the gravitino, if it's more massive than the lightest neutralino, can decay to a photon and a neutralino. And if the mass hierarchy is reversed, the neutralino will decay to a photon and a gravitino. In our case, since our parity is broken, the gravitino could decay directly to standard model particles. In particular, there exists a diagram where the gravitino can decay to a photon and a neutrino through the mixing of the neutrino with the photino. This decay is twofold suppressed. It's first suppressed by the gravitational interactions and the big scale of the Planck scale, and also is suppressed by the smallness of the breaking of our parity. These two things together makes possible for the gravitino to be stable enough to be dark matter. In particular, what takes values for the mixing between photino and neutrino that are typical for the neutrino CISO to work, and takes a mass for the gravitino of the order of 10 GeVs, the proper lifetime of the gravitino is orders of magnitudes above of the age of the universe. So it is stable enough, the gravitino, to be considered stable at cosmological scales, but it is still decays. That means that the decays of the gravitino will produce gamma rays that could be seen at gamma ray searches. Since the gravitino is decaying here through a two-body decay, the signal could be a monochromatic photon that is fixed by the mass of the gravitino completely. So, for example, one could put constraints on this model from Fermi lab searches to gamma rays, and in particular, one can put an upper bound on the mass of the gravitino, 17 GeVs, and a lower bound on the proper lifetime of 4 times 10 to the 25 seconds. Just a reminder here to stress a bit more that through this parity breaking that is related to the Gaussian CISO, this expression is connecting the phenomenology of dark matter to the process giving mass to neutrinos. So here is the key part of the model is really the neutrino CISO. So now just a bit of an outline of how the phenomenology at collider works for this model, because it's a bit different from other models. Since our parity is broken, it doesn't happen as in the typical supersymmetric models with our parity. The signal expected at collider is not missing energy. Here, when at collider some SUSY particle is produced, this SUSY particle will always prefer to decay through not suppressed amplitudes to producing the LSP in the decay chain. And finally, this LSP that is a bottleneck in the decay chains will decay to standard model particles through our parity suppressed amplitudes. That means that typically the signal at colliders, regardless of which particle are you producing, is the presence of some long-lived particle signal. It depends on the specific point in the parameter space, but it's the typical signal of this model. So going back a bit to the neutrino CISO, that's I have said is the key part of the model. We have studied that when one chooses to have only diagonal Yukawas, which is something convenient, not only because it makes the model simpler, because the model has too many parameters from start, but also having non-diagonal Yukawas is not very safe assumption, because these off-diagonal Yukawas typically can induce flavor violating processes in low energy observables. So it's quite constrained. So assuming diagonal Yukawas, which makes the analysis simpler and is more safe from low energy perspective, there is three families of solutions to three let's say regions of the parameter space where the CISO gets the correct neutrino physics. The first one happens when the Gaussian masses are negative. That means the Gaussian masses has a negative sign with respect to the rest of the terms of the Lagrangian. In that case, with neutrino Yukawa coupling for the first generation being smaller than the other two, and the first neutrino getting a bit higher than the others, a mild tuning between the two first terms of the Gaussian CISO is enough to reproduce the correct neutrino physics. And this family of solutions generally have one of these neutrinos to be lighter of the other two. And this is the first generation of neutrinos. The second solution is when the Gaussian masses are positive, and now the third generation of neutrino Yukawa couplings is the smallest one. and now the first neutrino web is the smallest one. In that case, the seesaw is dominated by the Gugino part, the second term in this expression. And now what we expect is that the third generation of neutrino is the lightest one of the three. And the third family is works the same as the second, but interchanging the second and the third generation of right-handed neutrinos. So with this in mind, it's kind of natural to expect that the leftest neutrino is the lightest of the particles in the SUSY spectrum. Okay. So a bit of a summary of what is as neutrino. So this neutrino comes in an SU2 doublet. It's a complex scalar. So we have a CP odd and a CP even part, which is almost degenerate in mass. The leptons came with the neutrinos, normally with a bit more of mass, around 10 GeVs or so, coming from a D term. And if we neglect small terms, meaning small here, typically that are suppressed from the smallness of the particle violation, one can get an approximate expression for the mass of neutrinos, which is presented here. At first sight, one could think that this mass has to be very small because it has a value of the neutrino Yukawa coupling here, but it also has the web in the denominator. So this fraction is actually order 1 typically. It depends on the specific solution of the seesaw, but it's around 1. So if one takes values for the rest of the parameters on the SUSY scale and takes this fraction being order 1, is enough to have a slightly smaller value for A nu to have a lightest neutrino. Typically, for example, for A nu being minus 100 GeV, one get a mass of the leftest neutrino on the electroweak scale. So with a neutrino of this mass, we have explored the parameter space, and we have seen that for both CP odd and CP even, if the mass of this neutrino is below 100 GeVs, here, most of the parameter space leaves a long-lived neutrino. There is a region here, especially for small lambda, for higher masses, where it can be prompt, but most of the parameter space point for a long-lived neutrino. So with this phenomenology in mind, we propose two ways to detect this LSP. If it were prompt, if it belongs to the first two generations, it can be clearly seen in events with a couple of photons plus missing transverse momentum. If it's from the third generation, it's easier to see in diphoton plus dilepton events or multilepton signals. And if it's displaced, the most promising signal will be the Drell-Yan production of a couple of neutrinos, decaying each of them to a couple of leptons. These displaced dileptons that happens in most of the parameter space again when this is a tau left neutrino, meaning displays normally being about the 100 micrometer scale, more or less. So this can be compared with Atlas searches for displaced leptons. Okay, this is an example from native research. The most important selection here is the one that requires that the two tracks associated to the leptons has to reconstruct a secondary vertex that is at least 4 millimeters away from the first interaction point and not more than 30 centimeters. That means that it has enough hits in the inner tracker. This analysis has, however, one subtlety, that is since it's designed to look for particles that can decay at a distance that can be so large from the first interaction point as 30 centimeters, has a problem with the trigger. That is, the triggers normally needs the full information from the tracker to separate backgrounds. And instead, the trigger used for this analysis only use the calorimeter information. And to separate backgrounds from particles not coming from the first interaction point, they have to use very harsh thresholds on the energy. In particular, they require for each event to be recorded to have at least one muon with 50 GeVs on energy, or one electron with 120 GeVs on energy, or two electrons with 40 GeVs. In the analysis, they found no displaced lepton events, and this is compatible with their prediction for backgrounds, which is of the order of 10 to the minus 3. And we can use this to put constraints to our model. We make first an analysis including only one generation of neutrinos to make the analysis simpler. And we found some possible exclusion. This panel in the left shows how the parameter space in Gaussian mass and lambda is excluded. The region, each number points to a mass for the leftest neutrino, and the region above and to the right of each colored curve could be excluded. The thickness of the line represents the uncertainty. And for example, for 100 GeV neutrino mass, that means that we can exclude masses of Gaussianos down to 3 TeVs, more or less. Then we propose a new analysis. In our model, we have predicted before that, in general, the decay length of this neutrino is always within 1 centimeter, okay, in most of the parameter space. That means that we can use the standard triggers. For example, the trigger for muons requires that, if I remember correctly, requires that the tracks has to have an impact parameter that is not longer to several centimeters. So in this case, only for this kind of analysis, we can use the data recorded for with the standard triggers and pass the same analysis, but with more data. We expect that this will be still a background-free analysis, because what we see from the Atlas data is that the number of standard model events passing from one trigger to the other, the number of recorded events is a factor of 10 higher. This, since the background predictor is 10 to the minus 3, and that will be 10 to the minus 2, that is still compatible with 0. And in that case, we see some optimization, some extra exclusion in the analysis. For example, now for a 100 GeV neutrino, we will be able to exclude masses of Gaussian masses up from 2 TeVs. So next step has been to make the full analysis, including 3 generation of right-handed neutrinos. We have scanned over all the parameters relevant for neutrino phenomenology. We have imposed constraints from the neutrino physics, from his physics, several flavor observables, the stability of vacua. And we have made 2 scans with 2 different values of tangent beta, one focusing large tangent beta around 10, and the other one with low tangent beta. And the points we have get from this scan, first let me compare this with the predictions in previous slides. So this was the approximate expression I have given for the mass of this neutrino. So after the scanning the points, we have seen that indeed this behavior happens. This blue circle is represented here in the horizontal line, and increasing the value of this fraction increases the value of the mass of this neutrino. And also getting more negative value of A nu makes the mass of this neutrino also bigger. And the most important part, again, is the neutrino CISO. We can see from the points that the solutions found are in the family of the second solutions. We can see here in the horizontal line, in the horizontal direction is plot the third neutrino Yukawa coupling. We can see that going in the x-axis that doesn't change the rest of the parameters, which is interpreted that this Yukawa coupling not playing a role in the solution of neutrino physics, but going to higher values of the neutrino web requires higher values also of the Gaussian mass. This is points to the same expression that we have here, where higher values of this neutrino web needs a higher value of Gaussian mass to get the same value in the effective mass. And finally, okay, here is it. We see also the hierarchy in the Yukawa couplings. We see that the points we get have the third generation of neutrino Yukawa couplings being the smallest one, and the biggest one being the muon one. This have a direct implication for the phenomenology of the neutrino, because since the dominant part of the CISO is the Gaussian part, that will mean that the main decay channel of this neutrino will be the neutrinos. Okay, this is an invisible decay, not interesting for long-lived particle searches, but we still have the visible channel of this neutrino decay into leptons, in which the most important one will be the decay to muons, because the biggest neutrino Yukawa coupling will be the one of the muon. So
Iñaki,
yes?
you have about 5 minutes left.
Okay.
5 minutes.
Well, this is just let me summarize this very fast. These are the results in the top part from the scan 1 with lower tangent beta, and the lower part from large tangent beta. The light blue and red points are points already excluded by LEP, and no point can be excluded with present displaced vertex searches, but with the optimization that we propose, we are able to exclude the dark red points. So not a very powerful exclusion power, but some points can be excluded, especially in the region of masses below 80 GeVs. So now the third part, which is the case where we exchange the solution on the CISO. Now we don't focus in the case where we are in the second family of solutions, where the lightest neutrino is the tau 1, but now we go to the third solution where the muonest neutrino is the LSP. That means that we don't have visible channels for the decayed neutrino. Then direct detection is not really interesting, because the only possible to see direct production of this neutrino will be through monojets, and it's not possible for this kind of particles. But we can still study the effects of these lightest neutrinos in the anomalous magnetic moment of the muon. So we have the usual expression from an SSM. There is a small difference from our models. There are singlets in the model, but we push the mass of the singlets and singlinos up, so the expressions could be similar to the ones from an SSM. It's known in general that we need masses of the electroweak SUSY particles to be around the electroweak scale to have a significant contribution to the G-2. We have found some points that coincide with the experimental value of the G-2 if the masses of this neutrino are not much above 300 GeVs. So we now apply to these points we have found the experimental limits from LHC. We divide the points in 3 parts, depending on which one is the LSP. This triangle represents parts where the Vino is the LSP, and then is the Wino. The crosses represent points where the Vino is the LSP, and there is then is the neutrino. And finally, the dots represents points where the LSP is the long-lived neutrino. So in each case, we can apply different searches. For example, in the case of a long-lived neutrino, since the neutrino is going to decay invisibly, this can be compared to lepton plus missing energy searches at Atlas. This is a powerful search. It can constrain much of the parameter space, but in the region where the masses of Wino and neutrino are closed, the exclusion power drops. It's not so efficient. In the region where we have triangles, we focus in the detection of long-lived Vinos that will decay through leptons or quarks plus leptons, with the addition, with respect to the previous search for long-lived particles, of extra prompt particles coming from these gauge bosons. This would make easier to pass the trigger requirements, and probably the searches are more effective than before. The caveat here of this search is that if the proper decay length of the Vino is close to 1 millimeter, the exclusion power of this search is very low. And finally, we have the central region with crosses, where the signal is similar to the previous case, but we have also this neutrino in the middle of the decay chain. Some cases where there is enough energy between the masses of these particles, this will mean more prone particles to trigger the event, but also could mean that if the spectrum is very compressed, to make it more difficult to be detected. So we apply these constraints to our first scan. What we have seen is most of the points are excluded. It's important to note here that we have imposed a gut-inspired relation between M1 and M2, and also that we have chosen an effective mu that is 379, if I remember correctly. Only few points survive, some of them here because of the proper decay length of the Vino is very small, and some here because when the mass of when M2 becomes bigger than effective mu, these points really are excluded because of the Higgsino production, not because of the Wino. But these points here are points where the Higgsino and the neutrino are very compressed and cannot be seen. So we dropped some of these assumptions to see if some points can be recovered. We actually have seen that we have plenty of points. If we free the value of M2 of M1, especially these points happen because with the new values of N1, the proper decay length of the Vino is shorter, and the displaced vertex search is not constraining for these points. We also recover these yellow points because they were excluded before by too light Higgs-Sinos, but now with Higgs-Sinos in 800 GeVs, these points are recovered. So just to summarize a little bit, this mu SSM is a well-motivated model that solves the mu problem and gives masses to neutrinos with the same mechanism. The central part of the model is the neutrino CISO that motivates the R parity to be small. That means that for having a dark matter candidate, you need to go to the gravitino. And with the natural solutions to the neutrino CISO, one gets that is motivated to have these neutrinos to be the LSP. We have proposed several channels to detect the tau leftmost neutrino as the LSP, and we have seen that the light muonous neutrino cannot be directly detected, but can produce an important contribution to the G-2 enough to close the gap between theory and experiment. And many of the points where this is possible are still allowed by LHC. Thank you.
Thanks a lot for this interesting talk. Unfortunately, we can't hear everybody clapping. Are there questions for Iñaki? Maybe I start with a question to give people more time. Well, actually, I would have two questions, but let's start with one thing that you have touched upon only in the beginning, where you are making the connection between the dark matter candidate and the neutrino physics. My question is, in which way, apart from measurements like at Fermi-Lat, can we get more restrictions on the allowed parameter space for the gravitino? Does the collider phenomenology that you presented can be connected in any way to the gravitino phenomenology? I guess not, but how can we learn more about it?
I mean, obviously it's connected because it's connected through this mixing, but the range in which this mixing can vary is not large. It's quite constrained. So in this expression, there is way more freedom to play with the proper lifetime with the mass of the gravitino. I mean, I think it mostly depends on which scale you choose for the neutrino mass. If, for example, you allow for neutrino mass to squeeze these masses in the lower value possible for the masses, then normally you get a smaller mixing between the photino and neutrino, and this will probably mean a bit larger proper lifetime. And if you go it in reverse and get the neutrino to the upper limiting masses, you get a slightly lighter proper lifetime. But it's not buying you a lot of space. It's probably a factor of 2 or 4, something like that. Instead, you have a factor of, I mean, the gravitino mass is going with a power of 3. So a small change in the gravitino mass is making much more effect here.
Mm-hmm. Okay, I see. Yeah, it's difficult to connect it. I understand.
One question, in your still allowed parameter space, do you have parameter regions where you get very displaced vertices? And could this be explored by, for example, Mathusla or other proposals for very long distance displaced vertices detectors?
The problem here is that for having a correct G-2, you do not only need the LSP to be light. You normally need both M2 and this neutrino being light. So if you want, for example, the LSP to be very long-lived, to see, for example, at Mathusla, you can make the Vino very, very displaced. This is possible. But probably you have to push the rest of the masses up to have some extra kinematical suppression. But then probably you are not making much in the G-2. So here, the thing is the range, the proper decay length, the range for this is a scale of millimeters. You can probably not go much further than 10 millimeters.
Okay, I see.
No chance for Mathusla then.
No.
Good. I don't see any hand raised. Thanks again, Iñaki. Please stay here for possible later questions. And we come to the last talk by Thomas.
Hello.
Yes.
Wait, I try to start sharing. And try to get this on full screen.
This looks very good.
Okay.
We have 25 minutes to talk about pseudo-Nambu Goldstone bosons and composite Higgs models. Please.
Thank you very much. First of all, I would like to thank the organizers for putting together this very nice workshop, which we unfortunately can only have online, but I think it was a very nice and successful week, and there were many interesting talks. I'm going to talk about composite Higgs models and light states you can have in composite Higgs models, which is based on a series of work where I've been working on the pseudo-Nambu Goldstone bosons and also the connection to vector-like quarks, but those I will mention only in 1 or 2 slides at the very end. So let me give you the outline. I'll first give you a motivation for composite Higgs models and in particular why it is likely that you have additional light states in those models. Then discuss the phenomenology of 2 types of PNGBs which appear in a larger class of models. One is a standard model singlet, which interacts only via Wessel-Witten terms, and one is a color octet. And I will also comment on the status of searches for other PNGBs in those models. And then, as said, in the end, I'll have a brief remark on the impact of those PNGBs also on the phenomenology of vector-like quarks. So as a motivation, the idea of composite Higgs models is very old. It's an approach to the hierarchy problem where the idea is to basically solve the hierarchy problem a la QCD, i.e. in QCD, nobody is asking why the QCD scale can be so much smaller than the Planck scale, because it comes out of running of a gauge coupling, which becomes strongly coupled at an exponentially smaller scale than the Planck scale. So the idea here is to have a new BSM gauge theory which becomes strongly coupled at a few TeV or 10 TeV. And you want to realize the Higgs multiplet as a pseudo-Goldstone boson multiplet of a global symmetry when this new gauge theory condenses. So in that way, you explain the hierarchy down to TeV purely by dimensional transmutation. And you can also establish a smaller hierarchy between the TeV scale down to the decay constant f of this particle, which just because it's a pseudo-Nambu Goldstone boson, so it's naturally lighter than the cutoff of your scale. So the price to pay if you want to realize such an idea is that you have a strongly coupled theory at a few TeV. So at that scale, you would expect additional vector resonances, vector-like fermions, new scalar resonances, very much like bound states in QCD around the QCD scale. And it might be that you don't only get the Higgs multiplet out of the global symmetry breaking structure, but that you also get additional pseudo-Nambu Goldstone bosons. And I'll show you in the next slides that this is quite commonly the case if you want to build a realistic model. In addition, you also get at the scale of a few TeV higher dimensional operators, and you get deviations of Higgs couplings from their standard model values. And those are typically controlled by powers of the ratio of the electroweak VEV over this decay constant F. And precisely from measuring deviations of Higgs couplings and also from electroweak precision constraints, this scale F has to lie nowadays above around a scale of 800 GeV. And to answer one question of Sven, he will ask already, yes, there is a fine-tuning in those models, and this fine-tuning is basically, or one fine-tuning is basically parameterized by V over F squared. So the models are not 100% natural. You have a small fine-tuning problem, very much like in any TeV scale model, just from having the electroweak physics low. So if you want to build underlying models, because so far I just said there is some gauge group confining and there are some global symmetries, here is a wish list which has been brought up by Gabriele Ferretti, and some starting work of this has been done by Tony Gargetta, of what we could want to have from an underlying model for a composite Higgs. The first one is we don't want to have any elementary scalars because scalars come with a hierarchy problem. Simple hypercolor group. We must have the Higgs candidate amongst the pseudonumber-Goldstone bosons, i.e. some multiplet with the right quantum numbers to be identified as the Higgs. We also want to have a vector-like top partner amongst the bound states. This is mainly because in order to generate the Higgs potential, we need some explicit breaking. And a very popular mechanism is to have the top elementary top mixing with some top partner, which gives you an explicit breaking and generates the Higgs potential. And it's also a way of giving a mass to the top, which we can't do in the same way as in the standard model, because now the Higgs is a non-linearly transforming object. And what is common to all those models is that all models contain several top partner multiplets, not only one. And in all models, beyond the Higgs multiplet, there will be additional PNGBs, some of which are electroweakly charged, some of which are even colored. And there is one which is a standard model singlet. I show you one example, just so you can see how those models are built up. So here there is an example based on an sp2nc gauge group. And you have two types of fermions, psi and chi. And you take 4 fermions in the fundamental psi, which have a global SU4 symmetry. Now, if you get into the strong coupling regime of your gauge group, then you will form a psi-psi condensate, which breaks the SU4 down to SP4. And from this coset, you get Goldstone bosons, and the Higgs is one of the Goldstone bosons in that set. You also want to have top partners, so you somehow need to get color into the game. And for this, you have those 6 other fermions in the antisymmetric representation. They also condense to a chi-chi, and you get a breaking from SU6 to, in this case, SO6. So you get additional pseudonumber Goldstone bosons, which are colored. And here in the lower table, you see the bound states of the model, where in the first 2 lines, you see the representations of SP4 and SO6, i.e. the unbroken global groups, where you see you have colored pseudonumber Goldstone bosons as well as the Higgs plus 1 additional state. And below that, you see the fermionic bound states, where I marked the states which contain potential partners for the top left and for the top right to mix. So basically, from the underlying gauge structure, we can determine at least the quantum numbers of the pseudonumber Goldstones and also of the top partners. Here you have a list of models where you can get a Higgs and top partners, and they are classified in terms of the global symmetry breaking groups. So it's basically SU4 broken down to SO4, SU5 broken down to SO5, sorry, SU4 broken down to SP4, or you have SU4 cross SU4 broken down to SU4 diagonal in the electroweak sector, and analogously you have assignments in the strong sector. Now let me zoom for those models into the pseudonumber Goldstone sets. In all models, you have one standard model singlet Goldstone boson, which is common to all models. And this just comes because you have, with the psi-psi and the chi-chi states, you have 2 U1A global symmetries. And now one linear combination of those 2 U1A symmetries will get a global anomaly because of the group which becomes confined. So this is very much like the eta prime in QCD, but you have one orthogonal linear combination, which stays a anomaly-free U1, and this gives you a pseudo-Nambu Goldstone boson. And this just comes from the fact that you have two types of underlying fermions. In all models, you also have in the colored sector a color octet. And then in addition, you have in the electroweak sector some extended electroweakly charged PNGBs. And in the color sector, on top of the octet, in some models, you have a color sextet as well as a color triplet. Here you see the rough bounds you have on those models, and I will discuss those first two more because we did quite a bit of work on it. Let me just say for the electroweak coset, you would expect bounds of the order of 200 GeV or even weaker, and here the relevant bounds mostly come from LEP actually, because those particles only interact electroweakly. For the color coset, as a rough estimate, you would expect bounds of the order of a TeV, but I will come to this more later. So let me come to the standard model singlet first. We can write down an effective Lagrangian for the standard model singlet, which is a PNGB, so it has a kinetic term, some mass term, which has to come from electroweak breaking. You have Wessomino-Witten interactions with the standard model gauge bosons, and interactions to fermions, which must be proportional to the fermion mass because they have to come from a derivative interaction. Now, with the underlying models, you can actually calculate those anomaly coefficients in the Wessomino-Witten interactions, so you can relate all those couplings to each other in one underlying model. So from the fact that you have an underlying model, you can really relate all those coefficients such that the only free parameters in the end are the mass of the pseudo-Nambu Goldstone bosons, which has to come from explicit breaking, and the decay constant f psi, which is however related to the compositeness scale of the Higgs. So this is the same f, or this is an f related to the scale, which should be of the order of 800 GeV or TeV. Now, as we can relate all those couplings for one given model, we can look at the branching ratios into all those different states. The production of this state will mainly be via gluon fusion. And what you see here is a plot where on the x-axis we have the mass of the what we expect light scale anomaly-free particle A. And on the y-axis, we left it as a free parameter, but this you would expect to be heavy, the eta prime. And we collected all the different bounds you have from dijet searches, diphoton searches, to boson searches, mu, TT bar, and there are also couplings to ZH, for example. And we translated those bounds as a bound on the scale f psi. And this is the current status you have from searches, and you can see that the bound, depending on the mass, is not very high, is way below a TeV, and you also have a quite prominent gap in the low mass regime, basically below the Higgs or Z mass. If you zoom in, so this was the plot for one model. Branching ratios for other models differ a bit, but here I zoomed into the low mass region, and I show you the line for 12 sample models, where you see that the bounds above or around the Z scale and above vary quite a bit, but you have this gap below 65 GeV for basically all those models, because you don't have any searches sensitive to this light mass regime. And we were also going through the projected searches by the experimental collaborations, as well as some proposals. We proposed the search in the di-tau channel. There have also been proposals for low mass diphoton searches. So this would be the coverage you could get at high luminosity LHC if all those searches are proposed. And you can see that you can effectively test and cover this parameter regime if those searches are proposed. This is just for one model, but I have the plots in the backup slides, which are online for all the other models as well. So the upshot from this is basically that you can have a light pseudoscalar in the overall mass regime, and that high luminosity LHC can test this area, but it's far from being excluded. Let me jump to the color octet PNGBs. Here you have the effective Lagrangian. Again, you have a mass term from explicit breaking. You can have a coupling to TT bar. You can have Wessel-Mino-Witten couplings to glue-glue, or to gluon and a U1Y gauge boson, which will give you a coupling to glue photon or glue Z. Now, we again know quite a bit from the underlying models. We can relate those, we can calculate those anomaly coefficients for the coupling to glue-glue and for this mixed coupling, and in particular from the underlying charges of the underlying fermions. There are only two cases for the branching ratios into glue-glue, glue photon, and glue Z. And in those two cases, either you have, so glue Z is always subdominant, but either you have 5% decay rate into glue photon, or you have almost 20% into glue photon as compared to glue-glue. In addition, you can have decays into TT bar, where you can estimate this, this parameter, but there is more freedom. So TT bar is a kind of independent decay channel. So now if we look into current constraints, for pair production, there are searches for tops, and there are searches for pairs of two dijet resonances at 8 and at 13 TeV, which we can use. We can translate this into a bound, and basically for the models, we only have the ratio of the coupling to tops and gluons as a free parameter, and then the mass of the PNGB. And what is excluded here is to the left. So you can see that for the models, you have, if you have a high branching ratio to TT bar, you get a bound of a bit above a TeV. And for dominant decay to glue-glue, you get bounds of the order of 800 GeV. So there are bounds in the TeV range, but there is still a lot of parameter space which is testable for the LHC. You can also do the same for single production. There you get more model dependence because the production mechanism depends on the model, but we also use searches for TT bar, dijet resonances, or jet photon resonances. You can translate those into bounds of the production cross-section, basically. Interesting for this point is that from the models, you expect TeV scale masses. Those are the contributions to the masses from QCD corrections. And we only start to probe this parameter regime now. For pair production, there are currently only bounds for two dijet resonances. For tops, actually, the latest searches don't look for high momentum top pair searches anymore. So you need to recast the Atlas and CMS searches, and you give up quite a bit of sensitivity by just looking for tops and not for boosted tops. So there is a possibility for improvement. And in particular, in those models, you can also get a substantial branching ratio of the new resonance into glue photon. So this could give you new signatures. And we did a study where we basically took the CMS study for pairs of dijets, and we asked what would be the sensitivity if you replace one of the jets by a photon in order to look for the decay channel into glue photon. So we basically took the search criteria of this search over 1-to-1, but just modified and replaced one jet with a photon. And I won't go into the details, but here you see the answer. What you see here is we left the ratio or the branching ratio into glue photon versus glue as an open parameter. We plot the range of masses here, and what you see in the light red area is where you have the highest sensitivity from the CMS type study for jets. What you see in cyan is the best sensitivity for two jet photon pairs, and in between you have a small area where you have one jet photon pair is most sensitive. And what you see in the contours is the luminosity you need at LHC in order to either discover or exclude this particle. So you can see that the two horizontal lines you see, those are our two reference models where you have underlying particles with hypercharge 1/3 or 2/3. So you can see that for branching ratios above basically 10%, this new search would really add additional exclusion or discovery potential beyond the two digest search.
You have about 5 minutes left.
5 minutes, okay. Then just a few quick remarks on the color sextet. Here, this is one more specific particle which you don't have in all models. This is interesting because the effective Lagrangian is very simple, and you basically only get a decay of the color sextet into two tops. This is not TT bar, but two tops. So if you produce the color sextet in pairs, you get again a 4-top signature, but it's not a, so it's one pair of top and one pair of top bar. We did a recast cast of a search which gives you a current bound of 1.25 TeV and a projected reach with 3 inverse autobahn of 1.6 TeV. And if you would see some signal in such a channel, this is a search looking for same sign leptons. You could easily distinguish this from a TT bar resonance because you get completely different angular distributions for the same sign leptons. This is the main upshot of this slide. Other PNGBs, I'll skip more comments here, but I just have it in here. So electroweak has not been studied in detail yet, but it basically looks like extended Higgs sectors. But it would be very interesting to really reinterpret the bounds from given searches. And for the color triplet, this is something we are currently looking into, which might also be interesting, but we don't have any bounds yet. And then a very quick remark, what could this do, or what does this have to do with vector-like quarks? In composite Higgs models, typically you want to have a top partner, and this top partner should not be too heavy, i.e. it should lie in the TeV regime. And Atlas and CMS have a very active search program for vector-like quarks, but in those searches, they are looking for charge 5/3, 2/3, -1/3, and -4/3 resonances, and decays into a top or a bottom and a WZ or Higgs. And you see the exclusions are represented in such triangles for the different branching ratios. Generic bounds are of the order of 1.3 TeV for those different particles and the different branching ratios. But if you have additional PNGBs, then those additional PNGBs open up new decay channels. And here you have a list of new decay channels through colored PNGBs or through electroweak neutral PNGBs, which have many possibilities to decay further. So now if you pair produce those vector-like quarks, you see that you get a zillion of new decay channels, some of which, or none of which is explicitly searched for. You can do recasts of existing searches in order to cover some of them. And here's just one example. Suppose you have a pair production of top partners and you have a decay into this PNGB, which occurs in all the underlying models, which dominantly, if it is light, decays into either glue or BB bar. Then you can look at what happens to the bounds from vector-like quarks. And if you have a decay dominantly into glue, then the bounds get massively weaker. So you can allow for bounds for vector-like quarks as low as 600 GeV. If you have a dominant decay into BB bar, then you get bounds of the order of a TeV, i.e. Comparable but not as strong as the bounds from the standard channel. And this is only one particular combination. So there are many new decay channels which wait to be investigated. So let me conclude here, and for time reasons, I think I'd leave the conclusions just on the slides. And
you have 1 minute left. You can
1 minute
conclude.
left. Okay, then let me just say composite Higgs models are interesting. They, as compared to SUSY, they suffer from that it is many things are hard to calculate, but the PNGB sector is well calculable because you can calculate it in terms of a nonlinear sigma model. They are way less phenomenologically explored than supersymmetry. I hope you can see from this discussion that it is quite likely that if you want to have an underlying UV model, you have additional light PNGBs. And I hope that you can also see from the discussion that the bounds on those PNGBs are weaker than one would naively expect. And the reason is not so much that you don't have coverage at the LHC, but that not necessarily all the searches are available such that you can easily recast them, and some of the searches are not being done. So this is the point I'm interested in to cover those searches. And finally, there are also many implications for vector-like quark searches because you add potentially many new decay channels. So then let me stop here and thank you for your attention.
Thanks a lot for this comprehensive overview. And I guess it's very difficult to cover all the different possibilities that this type of model really offers, yeah, and to get a coherent picture of the application of the current and possible future searches. Are there questions for Thomas?
I have some general question about maybe focusing on pseudo number Goldstone singlet pseudo number Goldstone boson searches. So in the context of a composite Higgs model, is there any some specific prediction of the coupling? I mean, for example, if we not just to give a constraint, but if we detect such a scalar fields, then can we distinguish those scalar would be originate from such as some composite Higgs model or related to UV model, or just a fundamental some scalar or whatever? Can you give us some comment about that?
Yes. So so here I have the Lagrangian again for this commonly occurring standard model singlet. And indeed, the mass we cannot calculate from the underlying model because it has to come from explicit breaking. So this we leave as a free parameter. But all the branching ratios in one given underlying model are fixed, meaning if I say I want to consider, let's say in this list, model number 5, then I can calculate those anomaly coefficients, and I also only have a finite choice of couplings for the couplings to fermions. I'm saying that because this depends on which top partner of the several top partners in this model the standard model top is mainly mixing with. So I get a choice, discrete choice of 4 possibilities basically for this model, also for the relative branching ratios to the top, which means if I measure this PNGB in one particular channel, for this model, I have a definite prediction for the signals in all the other channels. Okay. And so for one model, I basically just have one possible ratio of branching ratios. And in the minimal list, there were 12 models pointed out. Of course, this is not a proof that this is one of those models if all the branching ratios match. But at least it's something where one model gives you a specific prediction for the branching ratios into the different states.
Concerning this, I guess all these calculations have been done at the tree level because these models are not so well explored yet. Meaning, if you have this fortunate case that you measure one of these decays and you make the predictions for the others and you're off, but maybe you're off by 10, 20%, you might well be, this may well be due to missing higher order corrections also.
Yes, yeah? Yes, absolutely. So here we did the calculations for the branching ratios at tree level. And there is also one other slight fact behind, because this scalar really is a linear combination of the two U1 factors. And this mixing angle, or the diagonalization, so to speak, of those two U1 factors, this also involves one mixing angle where one also has to look for corrections. So maybe I should be more precise. You can calculate, and this you can calculate actually perturbatively, because it's the PNGB sector. You can calculate those branching ratios in each model. We calculated it at tree level right now. So yes, right now all the branching
ratios. Anybody try to do higher order corrections in one of these models?
We are not at the level of doing that, but it is not difficult to do in principle. Let's say
high order over what here?
So what this is doing right now is basically matching the anomalies.
Yeah.
But you have loop corrections to those terms.
But K, the best terminal return term would be quantized, right?
Yes.
So maybe there would be some correction of the decay constant F psi or C F phi or K phi H, something like that. But KG phi, KW phi would be just.
To those coefficients, you don't have a correction. But if you look at the production of this particle at LHC from gluon fusion, then you get corrections to those terms, and also to the, for example, from you also get contributions. You have couplings to TT bar,
right,
so you
right.
also get a contribution from, for example, a top loop.
Yeah, correction from correction of CF5, right?
Yes, yes. And so what we did for the cross-section calculation was we were taking the top loops into account, and we are currently working also for relatively low mass searches and resonances, and there we even take the bottom loops into account for the light mass regime. So those we have in. But it's not a full one loop calculation. So yes, you would need to go further if you find a signal there. And currently, if you find those branching ratios within 5 or 10%, one should do it at higher loop.
I wouldn't even exclude that the corrections can be as large as in the standard model, because this type of correction should exist here as well, I guess. And in the standard model, the corrections are at the 100% level for this particular process that you were mentioning, yeah?
For which mass?
For sure for 125, but I think this has been done for the whole mass range up to 1 TeV or so. So from very low masses to very high masses, and the corrections were huge anywhere. Yeah, I mean, there were also thresholds around the TT bar threshold or so, but you must see it at one loop already. But overall, the corrections were very large. Yeah. Are there further questions for Thomas? Nobody raises a hand. Let me ask one more question. You were not mentioning dark matter at all in your presentations. Do these models offer anything in this direction?
There are, so the models offer quite a bit in that direction, but it is more model specific, and I was focusing here on the PNGBs. The first thing is that, so if you go through the model list, then I think one of those models, the SU4 cross SU4 broken down to SU4 diagonal, contains one dark matter candidate, which is a composite baryon. So it's a 3-fermion bound state of the underlying fermions of this strong coupling group. You have in the Goldstone boson sector, not in those minimal sets dark matter candidates, but there are extensions, for example, for the SU4 to SP4 model to SU6 to SP6. And in those models, you have a dark matter candidate. And SU4 to SP4, you actually have something which people for quite a while claimed it would be a dark matter candidate. But with the underlying model, you can calculate the anomaly couplings, and you can see that this is a Wessumino-Witten anomaly. If you extend it to SU6 to SP6, then there is a preserved U1 symmetry which guarantees the stability of your dark matter candidate. So there is a number of dark matter or composite models which include dark matter candidates either as PNGBs or as heavy fermionic resonances, which are in the same type of style and which are mostly extensions of those models actually, meaning they share the same PNGB sector with additional states, some of which then are odd under a parity or have some discrete symmetry at least, which gives you protection of the dark matter candidate.
Okay. Andrew had a question, but then lowered his hand again.
Yeah, Thomas just answered it. He just answered the question before I asked.
Okay. Very good, very good. If there are no further questions for Thomas, thanks again. We now have still a little bit of time left, in principle, for questions to all the speakers, although I always found it a bit awkward to come back to this sometime afterwards. But if there are any other questions, don't raise your hand, just say whatever you have on your mind. And before we then stop the workshop, I would be happy if we could show ourselves again like we did on the first day, because then it makes it a bit less impersonal, these Zoom meetings. I liked it a lot when the first day we were more than, I don't know, I saw the full screen with different people. And I think it's very nice to see that we are here together. People keep appearing, that's nice. Good. So, yeah, even David is clapping his hands. How do you do this? Yes, very good. I don't see any raised hand or so. Yeah, nobody seems to have any urgent questions. Then maybe we can just, from the organizing side, say thank you very much to all the speakers, to all the participants. We sometimes had lively discussions, sometimes less lively, as it is, unfortunately, via Zoom, but I still think it was a worthwhile idea to have this little meeting between IBS-IFT and MultiDark to keep what we started a few years ago by these meetings between originally MultiDark and IBS. And I'm sure we want to keep this connection also in the future. And I guess there's a good hope that if we try to meet in a year or so again, it will be in person again. So thanks a lot. It's really nice to see all of you, and it would be even nicer to see you in person, and we try to do this next time. Yeah?
Right. So, yeah.
Okay, Marina is also here. Very nice. Good. Any other comments? No?
No comments. Yeah. So, also,
then, as I said, yeah, we'll meet again, and I'm looking forward to it.
Okay. So
okay. Yeah.
Then
thank you so much. Thanks, everybody.
I will then close the this meeting room. Okay. So
Thanks a lot, and we will have, among the organizers, I'm sure we'll have some evaluation of how it went afterwards.